Thank you. So bug fix, this is C3. C1 will not repeat to ISP2 the thing it has learned from ISP3. So ISP1 wants to send traffic to C3, but directly to ISP3, not in any different way. So how does a BGP router implement all the things we have seen so far? As we have said, BGP routers are connected to each other either across a border or inside a domain through TCP connection. Of course, BGP routers are not connected to other BGP routers who are not on link with them and are not in the same domain. So in the case that is here, A3 does not have a TCP connection to C3. Right? A3 and C3 are not speaking BGP with each other. They ignore each other. They don't know each other. So the only BGP interactions are the red one at the borders or inside the domain, the iBGP interaction. Okay. Wait. BGP messages are different from the way RIP is done by the fact that there are additions and withdrawals. So a BGP router, after some time, has learned some information, and its goal is to share that information with its neighbors, with its peers. With RIP, it does it periodically by always repeating the same thing periodically. That's a soft state approach. In BGP, we use what is called a hard state approach. Hard state means we synchronize the two information bases at the two ends of a BGP peering, and we exchange only the diffs. When something new has happened and it's an addition, then we send a new update, or something is modified, we send an update. When something is deleted, we send an explicit withdrawal message, which is very different from all other routing protocols. All other routing protocols, they learn that something is withdrawn by simply not seeing it anymore, with the exception of route poisoning. Here, when a route is removed, you have to explicitly remember to send it, which is bad. It's not crash safe, right? When you design software in a distributed system, you try to avoid those kind of things. You try to make sure that whatever my machine is doing, if the other guy crashes, reboots, and restarts and starts sending new stuff, then I can still continue the operation. Here, if a BGP router crashes and loses all the information, it will have an empty database. It will first need to get all the information from the neighbor, and only then it can send the withdrawals. Here is what a BGP router does in its life. It receives information from neighbors and stores it in tables that are called database, routing information bases. That's also different from RIP. RIP doesn't really have its own database because RIP manipulates directly the routing table. But BGP has a lot of information that is not yet in the routing table. In particular, there is what is called, let's see this picture here. This is let's say a schematic view of a BGP router. So it has on the incoming side one interface, one logical interface for every peer, in which the BGP router keeps a record of the last received message after applying the import filters. As we have seen, you may decide to kill some updates that you received. So you apply the import filters, and everything that you have received is kept here. If you have several neighbors, then you have several databases here. Then BGP applies, second step, what is called the BGP decision process. The decision process consists in comparing all the routes we have received and the ones that have not been rejected by the import filters, and keep only one. So keep only one route, depending on the criterion of the decision process that we will see in a second. And the route that is kept in what is called a local RIB, router information basis, or in practice it's directly put into the routing table of this router. Then the BGP router will inform the neighbors of what it has learned. But the important thing to realize is that this information is through the output of the decision process. In particular, a router informs the neighbors of only its best route. Typically, the internet has a huge amount of redundancy. Companies like Swisscom are connected to several tens of peers, so they have tens of possible routes to go to a remote destination. But they pick a Swisscom router picks only one as the best, and when it informs other routers, it will only inform them of their best route. So we don't propagate other information than the one we have chosen for ourselves. So it's like a sanity check. If I say something to you, it means that is the thing in which I believe. I don't give you a route that I have not selected as the best route. Then you put everything you export into a table, and the reason for putting in the table is to be able to remember what has to be withdrawn from what has to be advertised. So if I've given a piece of information to a neighbor and that piece of information changes, I go to my table to check that there is a change, and I will inform the neighbor of the diff. Here too we can decide not to export things by applying export filters. So this is what a BGP router does. The records that are called the routes, what are they exactly? Well, they contain essentially the network prefix, like we have seen in a routing table, plus the AS path, like we have seen in the simulations we did last hour, plus a potentially huge number of attributes and that are used to help the decision process, that are in some sense different priorities. Because as a BGP router, you will receive lots of routes from all possible domains in the world. You could explicitly route rules that say, I don't like Swisscom when I go to China, but I prefer Swisscom when I go to the US. You could write this explicitly in this form, but that is quickly very complicated. So instead, what you typically do, you give priority to some kind, to some decisions. And those priorities exist in various terminologies: wait, med, local pref. So those different things, we will see them in detail a bit later. They correspond to different type of policies or decision one might want to take. There is also a very important field, which is the next hop, which is the field that makes the link between internal routing and BGP routing. That will be an important topic we will discuss in a few minutes. BGP learns about the topology of the internet, but at the end of the day, we need to crystallize this into a practical decision. That is, if I have a packet to send to this IP address, where do I send it next? So how do we go from the fact that we know this address is served by this AS path? How do we go to the final decision? This will be using the next hop that we will illustrate in a minute. Before getting there, a few words on the decision process. So that's the code of a BGP router, if you want. The decision process decides among all possible candidate routes, and as I said, typically there are many possible candidate routes, which one is chosen. And only the chosen one will be further repeated. Of course, a route can be chosen only if it works. If it works, it means if the next hop on the route, I'll explain what the next hop is in a second, is reachable. A small caveat here: when we say routes, we mean prefixes, and different prefixes are different routes, even if one is a subset of the other. For example, 2.2/16 is a superset of 2.2.2/24. If I have those two routes, if I receive those two routes, and I have now an IP packet that starts with 2.2.2, I have two possible routes to go there. They are treated by BGP as different, so we will keep both of them. There is not the concept that the first one would kill the second. Although it can kill it, that's called aggregation, but if in principle they are treated as different routes. So for every route that you receive, you apply the decision process that is simply weighted, an ordered list of criterion. So we do, if you want, a lexicographic ordering of the routes by going through this list. So ignore this one. Local pref is a priority that's put by the first border router that has received the route, and is typically a tag of how much we like this interface. For example, Swisscom is connected to Sunrise but doesn't like to send traffic to Sunrise, for example, and we would put a bad priority to that for all the routes received there. But you still want to keep them because you never know, there might be failures somewhere in the internet. You might still want to use something you don't like or you don't prefer. So you first check this, which is a powerful and simple mechanism to give priorities that are statically configured in the BGP routers. Then, if you don't have priorities, local pref, or if all local pref values are equal for all the routes, you go to the second criterion that says pick the one that has the shortest AS path, which is an approximation of shortest path routing, as we have discussed a bit before. Then we'll see that a bit later. Then another criterion, if everything is equal, is if you have two routes that are equally nice from all viewpoints, you will prefer the one that you've learned from eBGP, from an external peer, over the one you've learned from an internal peer. We will see an example in a minute how it works. Then, if all criterions are equal, you will prefer the route that is the nearest next hop. By using this route, you will concretely go to a given next hop. Well, if everything is equal, you prefer the nearest one. And if everything is equal, then you still need to pick only one. So you pick, you break the tie by an arbitrary decision, which is the lowest BGP identifier. Routers have BGP identifiers, which are not the AS numbers. They are one IP address of the BGP router. Let's see on one simple example, very, very simple example, but that will really illustrate the very typical and basic operation of BGP. So in this simple example, there are only two domains, X and Y, and there are four BGP routers, R1, R2, R3, and R4, and there are only two prefixes that are being injected, 10.1/16 and 10.2/16. We zoom on R1, so we are here, and we see what happens when R1 receives some messages. So at the beginning, like in the lab, when you boot everything, all the information bases are empty. And R1 receives from R3, so R3 is the neighbor here, a message saying, I have those two routes, 10.1 and 10.2, and the AS path is Y. Right. So what will R1 do? Well, it will put them in its adjacency rib in. It will add the next hop attribute. What is the next hop? The next hop is an IP address that I can use to route if I adopt this route. So this route comes from R3, so the next hop is in fact the IP address of R3, which from the viewpoint of the domain X has to be considered as an internal address. The shared link between the two domains is in both domains. It has to be visible by the interior routing protocol, like RIP, of both domains, either by having R1 inject typically the prefix 111 in the domain of X, and R3 doing the same thing in the domain of Y. So those two routes have the same next hop. Note that the 10.1/16 is directly attached to R3, 10.2 is directly attached to R4, but it's a route that's inside the domain Y. So depending on how you configure domain Y, but typically in the standard configuration, R3 would advertise that route. So that's the first step. Then, of course, it applies the decision process. Now, I have two routes. For each of those, there is no alternative. If I accept them, if I don't kill them because I refuse the peering, I will accept them and mark them as peer. And then the job continues. R1 needs to export those to all its neighbors. Who are the neighbors of R1? They are all the routers, the BGP routers inside domain X. Here only one, R2. And also all the external neighbors like R3. So R1 will need to pass the information to everyone. Of course, to R3 will not pass it because it is coming from R3, and that's easy to see, in fact, because we have the AS path list. So one of the rules is you don't pass to someone in ASY a route that comes from ASY. So this route here, the AS path is Y. So I will not pass it to R3 because R3 is in domain Y. Otherwise, I'm creating a loop. So, but I will pass it to R2. So R2 will receive this information saying, I have a route to 10.1 and 10.2, and the next hop is this one, the yellow one here. So R2 at this point knows how to route to those two prefixes, and the direction in order to go there would be via R3 inside domain X. Okay, let's continue. I assume R2 that has received this from R1 in the meantime also did something that we have not seen. R2 probably has received from R4. R4 is here. R2 is here. The same process has happened in parallel at the other end of this network. So now R2 sends to R1, we zoom on R1 in this, those two messages, the same routes, 10.1.16 and 10.2.16, but with a different next hop. The next hop is this one. Before receiving, so this router will put it in its in database, which corresponds to the red lines here. Now the decision process will do something. What will it do? Clicker. Will it pick the new routes or no? Ten more seconds. And the correct answer is no. Why not? Well, because now we truly have to take a decision, so we have competing routes. Which one should we take? If we look at the newest, we apply the decision process. So what does the decision process? First look whether there is wait or local pref. There is none. Then we come to the criterion that says a route that is learned over eBGP is preferred over a route learned over iBGP. What does it mean here? It means R1 give preference to a route learned from R3 to a route learned from R2. The same route. So if for the same destination I hear it from R2 or from R3, then I prefer the one from R3. If all the other criterion are the same, which is the case here, therefore R1 will keep that one. It will ignore the one coming from R2. Which means in particular, all traffic that goes to 10.2.16, if it comes from R1, will go directly here, will go directly from X to Y instead of first going through X and then going back to Y. This is called hot potato routing. If you have something to send to another domain, you prefer to send it through the nearest interface of that domain, and that is in particular implemented by this rule here. Since there is no change, because the best route is the same, there is also nothing to send, because there is no delta in the out ribs, so that's the end of the story for this step for R1. So we see a difference here with RIP. If there is no change, then BGP does nothing. So it's a silent protocol if there is no change. Apart from a keep alive. There is a keep alive message that's sent once in a while, but you don't repeat the entire database if it's the same. If it's the same, you simply do nothing. Okay, that was our second simulation of the day. Let's go to the third one, our slightly more complicated network. I've added a router into ASX. And there are two physical links, which are the plain lines in ASX. And a dotted line means appearing. We zoom on ASX, and we see that those three routers are BGP peers because they're in the same domain, but they are not directly connected. So R22 has a TCP connection to R1 that perhaps goes via R21, but it goes via R21, not as BGP. R21 forwards it as any router does for any packet of any TCP connection. It doesn't handle and interpret the BGP messages that are contained there. Also, note that in this domain X, like in every domain, we have both IGP, for example, OSPF or RIP, and we assume here all link costs are equal to 1. That's another thing that's important to realize. With BGP, we don't save the interior routing protocol. So any domain has, in principle, RIP or OSPF or some interior routing protocol. If in addition you run BGP, then you have to run both. So the routers like R22, R1, they run both. They have two routing protocols at the same time that are running in parallel. That's why they need to be powerful machines. Right? Now let's assume that the announcements are the ones that are made in red. So we've changed a bit the rules. We see here that R3 announces only the local route attached to it. That's a different policy of the domain Y. And R2 announces also only the local route. Now R2 is connected to two routers in domain X, so it announces to the two routers. This is how the system is designed. As you will see in the lab, you can control which routes are announced. This is the choice that is done here by ASY. Right. So let's start the same simulation again. So we are zooming at R1 again. What happens when R1 receives from R3 this message? Now, like before, nothing exciting comes. There's only one. So I've reset the system, reboot, everything is empty. R1 receives only this message, keeps it, has no choice. Policy doesn't forbid it. Now it repeats it to two neighbors, because now it has two BGP neighbors to repeat it to. So R21 and R22 now have this information. Okay. Now assume that R22 sends to R1 this information. So R22, this router, has received this information, 10.216, with next hop 2221, and passes now the information to R1, as is the rule in any well-behaving BGP router. So now we have this route that is added. Again, there's no competition. because we have two different routes. So nothing happens other than now R1 will pass it along to no one else, because it could pass it to, sorry, it should pass it to R21. So they should add something here. No, it will not. Thank you. It will not pass it along. So this is correct. Because you don't repeat a route that you've learned internally. There was a comment or question? No, it will not, because R1 has heard this new information for R22. Whom could it repeat? It could repeat it to R3, but that would create a loop in the AS path, because that in route comes from AS path Y, so I don't repeat it into AS path Y. And I don't repeat it to R21 or R22, because they are inside the same mesh as I am, and we don't repeat internally what we have learned internally. Okay. So far so good, no big deal. Now let's continue. R21 sends to R1 the same information it has learned from from the neighbor here. So this one that has been learned from R21 sooner or later also reaches R1. Now we have an interesting case, because now for the route 10.2 we have two routes, one with next hop 222, 1, and one with next hop 3331. What will happen now? Which one will be chosen by R1? Which number is that? Five more seconds. And the answer is yes. It will pick the new route. Why? Well, that's the decision process. That was too early. The decision process will look through this, will go through this list of criterion. So we have received two routes from two internal peers that have simply different next hops. There is no weight, no local pref. They have the same AF path, so all of this is equal. There is no med here. They all come from IBGP, so everything is equal. Then we go to the the fifth criterion, or the last meaningful criterion, which is shortest path to next hop. What does it mean concretely here? Voila, here we are. The shortest path to next hop is either 3 or 2. We have to look at what happens inside ASX. Inside ASX, there are only two physical links, and then there are the border links. And the cost from R1 to 3 is 2. We go via one router. The cost from R1 to 222 is 3, because we need first to go via R22. Right. The router that is inside the router R4 is of course not visible for RIP from the viewpoint of the domain, domain X. The links that go to the outside are visible, but the routers that terminate the links are not visible. So there is no information inside X that we could go via R4, for example. So the shortest path is 333. That's the one we will take. So we will take it, and it will become the best path. Oops. 32. Last question. Another simulation. I have two ISPs that are peers. They consider themselves as equal weight. They have shared link costs. I have traffic that goes from customer 1 to customer 2. And assume the only interconnection between those two guys, those two entities, are the ones that are shown. I'm not showing the internal connections inside the yellow clouds, but I'm showing all the connections from one cloud to the next. Which path will be used by packets from customer 1 to customer 2? If we use default configurations in BGP. Five more seconds. Here you have to guess because in reality we don't really know. But I close in 5 seconds. The first path, R1 to R11, is the path that decides to stay longer inside the domain. It is this one. The second one is the one that goes first out. And if we use the configuration that is by default the ones we've seen here, this is what will happen. So BGP was done with the idea that's the default thing people would like to do. It's called hot potato routing. It has an interesting side effect. It's used a lot. It has an interesting side effect, is that if you apply the same thing in the reverse direction, packets that flow in the reverse direction will go a different path because, well, the same reason, right? So in particular, hot potato routing gives asymmetric routing in the internet. So that's one of the side effects of BGP. In fact, we cannot guarantee that routing is symmetric. So we cannot, if you try to spy all the traffic, perhaps at R22 you will see only one-way traffic for a lot of connections. Hot potato routing is done if you use the default configuration like we have seen on those simple simulations. But we will see a bit later that you can play with things like the local pref or the weights to do the inverse. In fact, some operators, typically the expensive operators that think they have very good networks like Swisscom, then they prefer to keep the traffic in their network for their customers because it will make their customers more happy because they think their network is better than the crappy whatever free or whatever competitor. So don't think that this is a general rule, but this is one thing that is quite possible and happens a lot in the internet. We have seen in those simulations also two different ways of bootstrapping or what is called originating the routes into BGP. In the first example, the router in the domain Y has advertised the two routes, 10.1 and 10.2. It has advertised the two to the BGP external neighbor. In the second case, one router advertised one route, the other router advertised another route. Both are possible. So the question in general is, how do you do things? Well, first, we need somehow to do something. We need to bootstrap the routes into BGP, because BGP learned routes. What we have seen is a way of repeating routes that we have learned. So somewhere we have to start this process. Starting this process is called originating. a lot of the difficulty in BGP is the terminology. So we'll try to keep a clean terminology here. And what we have seen in the example is perhaps a case of static configuration. Static configuration means you can go, and you will do that in the lab in 1 or 2 cases, you can instruct a router which routes to propagate to external neighbors or to internal neighbors, which routes to start from scratch, if you want. This is done in the tools we use with the network command. This is static, so like any static thing, you try to avoid it unless it's for very, very specific things, like default routes. In general, you prefer things that are more automatic. There are 2 ways, and the most natural way is called redistribute from IGP. What does it mean? IGP is the BGP word for the interior routing protocol. Why IGP? Because a routing protocol 30 years ago was called a gateway protocol. Today, the word gateway really refers more to an application layer gateway. We will see lots of them when we talk IPv4 versus IPv6, or a SOCKS gateway, for those of you who try to understand how Tor works. So this is higher layer intermediate systems. In the old times, gateway meant router. So IGP means the interior routing protocol. Goodbye. Now, what is the most natural thing to do? You are a domain. You run your RIP or OSPF. Through this mechanism, all routers in this domain know all the routes that are local, that exist in this domain. Then it makes sense to say to BGP, here are all the routes that exist in this domain. And this say to BGP is called redistribute. And in the lab, it's also the command called redistribute. So if you say redistribute RIP, that means that the router will go into the RIP table, will take all the routes that have been written by RIP in the routing table, in fact, and will declare them as routes that are directly attached to this network with AS path empty. This is one way to do. As you will see in the lab, you need to be careful how you redistribute. Very often, another way that is done in, I would say, the standard configuration is to redistribute only the directly connected routes. Directly connected means a BGP router knows what are all the interfaces it has, and all those interfaces, it will bootstrap, originate them into BGP. This works only if we are in a special case. In general, this won't work. In general, we need to redistribute RIP into BGP. But there are cases where this would work. Can you imagine one? Or can you imagine the problems that would cause if we use this in a general case? Well, imagine a network that has 20 routers, and every router passes to BGP the routes that are directly connected to it. For this to work, we must make an assumption that all routes are connected to, all prefixes are connected to a BGP router. If you have a part of your network, typically a backbone, an internal part of the network that does not run BGP and has a number of prefixes that are not directly attached to BGP routers, those routes will not be visible to the rest of the world, so it won't work. If you're in a case like this, you need the second method, redistribute from IGP. It turns out that in the base case, in the standard operation of BGP, we run BGP in all routers in the domain, believe it or not. Seems surprising. This is why this is often done, and this is what I call the standard BGP configuration, as you will see in the lab. A little point to discuss is aggregation and the side effects of aggregation. Aggregation is a good citizen policy. In the internet today, as you can see at the end of the presentation, I give the statistics of the number of routes of last week. And for IPv4 in the internet, we have 500,000 routes. For For IPv6, we have 20, 30,000, much fewer. Why are there much fewer routes for IPv6 than IPv4? So we have the bad reason. The bad reason is IPv6 is still anecdotal, so it's not taken seriously, and therefore there's not so many routes. That's a possible reason. I prefer to mention another reason, which is a good one, which is in IPv6 we can do a lot more aggregation. So for example, if you remember how IPv6 addresses are given, all the switch customers have addresses that can be aggregated to one single prefix, which is not the case for IPv4. So all the switch customers for IPv4, they cause in America, in backbone routers of the world, they cause one entry for EPFL, another one for ETH, another one for University of Bern, etc., because they're not in contiguous blocks. For IPv6, because the space is much larger, we can afford to make everything contiguous. So we expect this to happen, and we want this to happen. The bottleneck in the performance of the internet today is the size of the BGP tables. I mean, whenever there are problems anywhere, we need to transfer big tables that are 500,000 entries. Now, when there are problems in routing, if there are loops or inconsistent routes, for example, the parts of the internet are not reachable. So you may have a fraction of the internet that's not reachable due to routing protocol problems. So the more lightweight the protocol is, and in particular the smaller the table is, the better it will be. In order to make this happen, in order to make the number of routes smaller, we try to incentivize all operators to do aggregation. For example, if you receive an advertisement from somebody, imagine for a second that EPFL would run BGP and would advertise its IPv6 prefix, then an American provider that would receive this advertisement through a number of intermediate ISPs could compare it to an advertisement received from Switch and recognize that EPFL is a subset of Switch and then decide to aggregate them and therefore keep only one of the two, thereby reducing the size. Let's see practically how this could happen. Here is a small, yet another simulation, IPv6, because IP aggregation is a typical IPv6 topic. I'm assuming AS3, shown here, has received two routes, this one and that one. Is it possible to aggregate them? Quick refresher on IPv6, which I'm sure you love. I close in 5 seconds. So if you have a hardwired hexadecimal computer, then it's easy. Otherwise, I admit it's a bit more difficult. But the answer is yes, here they can be aggregated. Those two prefixes are in fact contiguous. Oh, no, sorry. The second, those two are contiguous, and they can be put together as any one of the two /47, which means we ignore the last bit. Therefore, if that is what AS3 does, so here is the explanation, if you look at the binary thing, then AS3 would not treat them as separate, but then there is a small problem. How about the AS path? Because AS3 has a path which is AS1, AS3 for part of the prefix, AS2, AS3 for the other part. Then BGP has a solution for that. There is a syntax of the path announcement that means OR. So typically, AS3 would send to AS4 this update. It would send this aggregated path. And the AS path is 3 followed by 1 or 2. This is how BGP hopes to make aggregation possible. Voilà, we'll stop here for today. We'll continue exploring BGP next week in the lab.